Okay, anyway, uh, did the recording start? Okay, fine. No problem. Good morning, everyone. Now, we have seen some of the elementary data structure, that is stacks, queues, trees, priority queues, graphs, even dictionary, that the binary search trees. Now, all these elementary data structures, what we have seen uh, is going to obviously you have had these topics, you have studied these topics in your data structures class, but we have seen again, we have seen these topics just as a refreshment for your future topics, or through we will be using them throughout the course. Now, especially graphs, which is used several places, queues are used in several of the algorithms, and even binary search trees, or I mean, mostly trees are used. Now, today in this session or in this topic, we are going to look at another data structure known as sets and disjoint sets and their operations. Now, this data structure, the sets and disjoint sets data structure, you have not seen in previous subjects or topics. So we will move on and continues to see what are sets and what are the operations that can be performed and their algorithms. Now, sets are nothing but they're set, they are a collection of elements. But remember one thing, in sets, we will not have duplicate elements. Suppose if we consider S as a set with 1 to 10 numbers. Now, this set doesn't contain a duplicate. The sets we are going to talk in data structure, in this algorithms or design analysis of the subject algorithms, is similar to your mathematical sets. Their operations are also similar, but we try to use a different structure to represent sets, which is going to be helpful for us in other topics or the future topics which we are going to cover. So S is a set with 10 elements, and remember, set doesn't contain any duplicates. Now, let us try to divide this set into three different sets. S is a set. We are dividing the set into three different sets, or we can call this S1, S2, S3 as subset of set S. So when we have this subset, you can find that S has got 4 elements, 1, 7, 8, and 9. S2 has got 2, 5, and 10, and S3 has got 3, 4, and 6. Now, if you observe, are these sets containing any common element? No, they are not containing. All sets have different elements. These sets are known as disjoint sets. These are known as disjoint sets. They do not have any common element. These are known as disjoint sets. Now, obviously, in mathematics, you have the operations of set, union of sets, intersection of sets, and other operation, difference, other operations. Those operations are directly applied on sets by looking at the elements and performing the operations. But here in algorithms, we represent sets as a tree. So set S1 can be represented as a tree where we have 1 as the root node and 7, 8, and 9 are the elements. So this complete tree consists of all the elements of set S1. 1 is known as the root node. The only difference between the tree and this tree, which we are using to represent sets, and the tree which we have seen earlier, or we talk about in data structures, the only difference between these two is that this set tree has arrows in the opposite direction. For example, 7, 8, and 9 are children of node 1, that is its parent. So instead of arrow going from node 1, that is parent to child, it's in reverse order. That is only the difference, nothing else. The other issue is that I am using, our textbook is using, the element 1 as the root node. You can use any node as the root node, it doesn't matter. We just have to represent tree, which will have we have to represent the set as a tree, which will have a node as the root node and all the other elements as its children. And remember, it's a tree, it's not a binary tree. It's a tree. Tree can have any number of children. Then for S2, we can use, for example, in this case, instead of 2, we have used, or even textbook has used, 5 as the root node and 2 and 10 as its children. Same way, node 3, set 3, 3, 4, 5, 3 we have used as the root node and 4 and 6, all the other elements as the children. So this is known as the tree representation of sets. Using this tree representation, we will be applying the different operations or algorithms. Now, again, let us consider these three sets. The set S1, that is 1 with 7, 8, 9, and then 5 with 2 and 10, and 3 with 4 and 6. Now, what are the operations that are there on sets? We have sets intersection, union, difference, and finding whether an element is there in the set or not. In algorithms, we are not bothered about intersection of sets, as well as we are not bothered about difference of sets, though they both give the same result. But what we are bothered about is union and find. These two operations, that is, we are bothered about union and find operations. So let us call this set 1, this as set 5. For example, because 1 and 5 are root node, that is why we are calling it as set 1 and set 5. Now here, suppose if I have to perform union of these two sets, what has to be done is we will take set S, the first set S1 set, and then the root of the second set, that is 5, can be made as a child of the root of the first set. So in this case, we are taking root 5 of the second set as the child of node 1 or root 1. So this whole thing is known as union operation. Or we can use set S2 and make the parent of S1, that is node 1, as the child of node 5. So this way we will be performing union operations. So this is how we are performing union operations. Now don't worry about what level it has or why the level increases. We simply have we simply make root of one set as the child of the other set. That is how we perform union operation. Now suppose if we have to apply union for this tree with node 3 as the root, we will simply make an union with S1. We will simply make 3 as a child of node 1. So there will be an arrow here and it becomes union of these 3 sets. Now, so this is how union is performed. Now, we have to be careful with one more concept. That is, when this is S1, suppose this is set S1 and this is set S2. When set S1, when we are performing the operation of union operation with set S1 union S2, once the operation is performed, they will not be set S1 and S2. When they are merged, original sets will not be present. So this is one more important thing we need to remember. So when we when we perform union of two sets, then the when we perform the union of two sets, we will not be having the original set. Now, you might be wondering, when we don't have the original set, then what happens? How are we going to refer them? Now, actually, what happens is when we have set S1 represented as a tree, S2 represented as its tree, S3 represented as 3, we will not be calling them as S1, S2, S3. We refer them by their root node, that is 1, 5, and 3. Set 1, set 5, and set 3. That way we refer it. Why? Because we can maintain a table. When we write a program, we can maintain a table. That table can contain the set name. So instead of calling this tree, the first tree as S1, second as S2, we can maintain a table. We can have set S1, and we can have a pointer to the root of S1. Then S2, we can have a pointer to the root of S2, as well as S3 with the root of the elements of S3, S3. So we usually don't call them as set S1, S2, S3. I mean, it don't represent them as that in computer science. But we can maintain a table, and table can contain set names and pointers to its root node. So this is how it is. The sets are maintained in an algorithm or when we write a program. Now, let us look at when we are saying it is maintained in a table. So obviously, when it is maintained in a table as this pointers, then obviously we have to use something to represent these trees also. That is this S1, S2, S3 in a program or in a computer. So for that reason, we will be using an array. Now, array has indices, and let us call this array as P array. We will be maintaining a P array. Now, when I'm saying P array, I'm just writing it as a row here to differentiate between its indices, and what are the values going to have in this P array. P array actually stands for parent. So we will be maintaining the parent of each node, so that we know, or we can construct a tree, or we know which element belongs to which tree and who is the parent of which node. So P array we will be maintaining. So I is nothing but the indices. Now remember, the index is not starting from 0, it's starting from 1. This is just because algorithms are not dependent on programming language. So we consider everywhere in whatever algorithms you're going to see, we will start the array with 1. Now, these indices actually represents the nodes. So index 1 means first node, index 4 means fourth node, index 7 means the seventh node. Now, suppose if we have 100 nodes, then obviously the length of the array will be 100, and we are going to have those many indices. Now, let us look at how we represent these nodes using an array. Now, node 1 is P will be containing the value of P will be containing the parent of that node. So when we have index 1, that means parent of node 1. Now, node 1 is the root. So it will not have its parent. That's the topmost node. So parent of node 1 or parent of the root is represented as -1. So we have for 1, we have -1. Then what about 2? Node 2. Node 2's parent is 5. So we will have 5 in the array at index 2. Node 3. Node 3 is a root node. So we will have -1. Node 4. Its parent is 3. So we have 3 in the array at index 4. Then node 5. It's a root node. So we will have -1. Node 6. its parent is 3. So we have 3. Node 7, its parent is 1. Node 8, parent is 1. Node 9, parent is 1. And node 10, parent is 5. So this is how an array is constructed, which is going to have the values of P, that is the parent of the node, and nodes are represented by indices, and each index represents a node, and the value of P at that particular index will be its parent. If there is no parent, that means if it's a root node, then the value will be -1. So this is the convention we use, or this is how we store these nodes in the array, known as an array, PI, parent array. Now, let us look at an algorithm. Now, this is the array we have already created. So this is for set S1, S2, and S3. Now, simple find. We are going to look at the find operation first. Simple find. We are calling it simple find because there is some complexity involved in this find algorithm. So that find we will look at in the later slides. But this is known as simple find to perform a find operation. Now, what this does is, when we call simple find of I, means if I pass find of 8, it means simple find over here, find of 8. That means I want to find who is the parent of node 8. That is what is find. Find doesn't, in sets, find doesn't mean that whether it is present or not. Find in sets means who is the parent of that node. Now, actually find means we want to know which set it belongs. So here I is there, then when find I 8 is called, what happens? What happens is I is 8. So we check P of I. What is P of I? P of 8. P of 8 is 1. Is it greater than 0? If it is greater than 0, what value is there in P of I? P of 8 has 1. So P of 8 is 1. 1 is assigned to I. Then again while loop executes, P of 1. What is P of 1? P of 1 is -1. Is it greater than 0? No. So we return I. What are we returning? We are returning 1. That means when find of 8 is performed, it gives us the parent. To parent of the set it belongs. So 1 is getting returned, so that means it belongs to set which has root 1 or set 1, this set. In the same way, suppose if we call 4. Now 4, directly using the array, you can see index 4, we have a value 3. So we go to index 3. Index 3, we have value -1. That means this element 4 belongs to set whose root is 3. Whose root is 3. So this while loop, what is it doing is it's trying to repeat itself because we have just have 2-level tree. A tree can be a large level also when we perform subsequent union operations. So the while loop executes looking at the indices and the p-value until p-value becomes -1. When p-value becomes -1, the index is the root of that tree to which that element belongs. So this is how simple find operation is performed. Now let us look at a union operation. I told you for union, the second set root can be made as a child for the first set, or first set's root can be made as a child to the second set to perform union. Both the ways you can perform. But here, a simple union algorithm or union operation, we are merging 2 sets. What we will do is we will make the set 1 root as the child of the second set. So the algorithm is very simple. We have to pass simple union means. Suppose I'm trying to perform union of 1, 5. And remember, for finding we can pass any element. Even parents element we can find to pass to find perform find operation. But in union operation we have to pass the root nodes. So here we are passing simple union 1, 5. So in 1, 5, when we pass 1, 5, what is happening is we are trying to perform union of the root node, which is 1, of a tree, root node of a tree, which is 1, and union of the tree, which has root 5. Now 1 and 5 is passed, so I becomes 1, j becomes 5. So j5 is assigned to p of I, that is p of 1. So in place of p of 1, what is p of 1? This minus 1. In place of minus 1, j5 is assigned. So what actually happens is we are trying to take the second root and second tree, and that tree's parent, that is 5, is getting assigned to the root of 5 is getting assigned to this root of first tree. So instead of minus 1, here we are going to have 5. Here we are going to have 5. So what happens is what is going to have one's parent, once 1 was the root. So instead of minus 1, we are going to have 5. So here you are going to have 5 over here. So what this means is p of 1. So parent of 1 is nothing but node 5. So always remember that when simple union is performed, it is the first set which is made, the root is made as a child for the second set. Now, these two, simple find and simple union, are very simple algorithms which just contain basic steps. Only three, as statements of only few statements. Now, if we analyze these algorithms, this is a while loop. It's going to run for at most, if suppose there are n elements and every element is parents the other elements, and at most we have to go, or this while loop will run for n number of times. So its time complexity will be O of n. And whereas this return I is a primitive statement, so it doesn't matter. So simple find has a time complexity of O of n, which is acceptable. Simple union, it's just a primitive statement. So its time complexity is O of 1. Very simple. Time complexity is O of 1, but it's constant. So these are the time constants, simple union and simple find. Now, these two algorithms we are calling simple because they perform very simple operations. But what actually happens is, in some scenarios, these two operations or algorithms will perform in a very, very worst manner. Our performance is not good for these two algorithms. So let us take a scenario for a simple union. Suppose if I have 5 elements and each element is disjoint. That means one is a set with itself. 2 is a set with itself. So there are actually 5 sets here. There are no arrows representing anyone. Now, so these are 5 sets. Now, if I perform simple union operation, let us take a table itself. I and P. I will be the indices, P will be the parents. So initially what happens, node 1, 2, 3, 4 and 5. The P value for everyone will be minus 1 because these are the only elements in the set and each one is a root of itself. So all will have minus 1. Now let us say we are performing operation union 1, 2. So what happens is I is 1, j is 2. So P of 1 is equal to 2. That means this P of 1 we are having value as 2. So for node 1, 2 is its parent. So we are performing union operation. So this is how union operation becomes. And now we have 1 and 2 with one set, 3, 4, 5 are elements of the other disjoint sets. Now suppose if we perform union of 2, 3. So 3 is j, 2 is I. So P of 2 is assigned 3. So P of 2 was minus 1 because obviously 2 is a parent. So 2 is assigned, we are actually merging them, performing union operation. So 2 is assigned value as 3. So what happens is now 2's parent, P of 2's parent is 3. So there will be a link created because 2 becomes the child of 3. Same way, suppose if we perform 3, 4. What happens at P of 3, 4 is assigned. So node 3 becomes a child, child of node 4 or 4 is the parent. And the same way, suppose if we have union of 4 comma 5. When we have union of 4 comma 5, P of 4 will become 5. So 5 will be the parent of node 4. So these are, and obviously 5 is the root node, and all are merged in one set. So there are no 4 sets now, 5 sets now. There is only one set with 5 as the root. So P of 5 is nothing but -1 because 5 element node 5 is the root. Now, what are we finding here? What we found is when union is applied successively in this scenario, we are getting a tree which has a larger height. So if we have n elements, that is n till n minus 1 and n element, then successive union operations at the end union n minus 1 of n will be, we will get a tree which will have a height of n. A tree which will have height of n. That is, as the number of nodes increases, we have each level where each node is at a level, and we have the height of the tree is, what do we call, n. Now, what will this whole thing, obviously union is taking -1. So now in this union, the complete n number of times we are running this union operation. So successive union operations when we perform, we have the time complexity as O of n. That is also acceptable, no problem. But what happens is, as the height of the tree has increased, simple find. If you use find operation now, perform find operation, find of 1, find of 2, find of 3, 4, so and so till find of n. Since find operation takes O of n, for the nth operation, find of n, it will be taking n times, because find of 1 means it has to start from this, go to this one, this loop, this, and so on, so till nth loop, and say nth time, and say that n is the root of this node. Even for 2, it has to run for n times, almost n times. So totally, we have the time complexity of successive find operations as O of n multiplied by n times, that is O of n square, which is quadratic time complexity. And this time complexity obviously is not acceptable. I mean, in this scenario, when we are saying simple find and simple union, it's though its statements are simple, but even its complexity has to be simple. But what is happening in this scenario, if you look at performing the successive operations, n number of times, it's becoming O of n for simple union, and for simple find, it's becoming O of n square. So for that, we have 2 more algorithms. Let us look at them. So again, let us consider that we have 1, 2, 3, 4, 5 elements in disjoint sets. Each element has its own set, so each element will be the root of that. So for every index, we are having -1 as its parent. Now we have something known as weighted union as a concept to to have a better performance for union operation. Both simple union and weighted union performs the same operation. It's going to perform union of 2 sets. But simple unions, as the case may be, its time complexity or its performance is not better. So that is why we have something known as weighted union. Weighted union, obviously, union operation takes 2 sets. So we have I and J's as simple union. So let us look at how this weighted union works. Suppose if we are calling weighted union for 1, 2. So I is 1, J is 2. So here what we'll do is we will use a variable temp, and P of I, parent of I, is added with parent of J. Now, what is parent of I? Parent of 1 and parent of 2. Parent of I and parent of J. So -1 will become -2. This is the value -2. Now we will have an if statement if P of I greater than P of J. That is parent of I greater than parent of J. Now here you might be wondering, every time parent means a root node. So if there is a root node, everyone will be having minus 1, minus 1, minus 1. So what is the purpose? We will come to know later. Let's just have a look at this statement. If P of I is greater than P of J. Now in this case, P of I is minus 1, P of J is also minus 1. So this is false. Else part we are having. Now in this else part, what we do is P of J equal to I. So what was I is 1 is assigned to P of 2. So P of 2, parent of node 2 will become 1 will be the parent of node 2. P of J. So here we have 1 and then P of J is assigned 1. So node 2 will have parent 1. So now we are going to have node 1 as the parent of node 2. Then we make the temp. We assign the temp value, that is minus 2, we assign to P of I. What is P of I? P of I is 1. Remember, we have performed weighted union 1, 2. So 1 is the root. So in place of root, instead of minus 1, we will be saving minus 2. So at this place, where here you will have minus 2. Now, before we proceed further, let us look at this. What is minus 2, minus 1? We have already said that minus 1 represents the parent, it represents the root node for a tree. Now, then what is minus 2? In weighted union, what we do is forget about what the value is, 2, 3, 4, minus, 1, whatever it is. If there is a negative sign, that means it's a root node. It's a root node. If there is a negative sign, it's a root node. Now, whatever value of that negative sign will be, that represents how many nodes are there in that tree. So that is why it is called as weighted union. That is called as weighted union. Now let us try to again perform this on 1, 3. So when we are doing 1, 3, what is happening here? P of I, P of 1 is minus 2, P of J is 3, J is 3, so minus 1, that becomes minus 3. Then again we compare if this is P of I is greater than P of J or not. Now sometimes it becomes greater, because that what this means is if two trees are there, whose ever weight is more, whoever has more number of nodes, that tree's parent, that tree's root will be the parent of the set which has less number of nodes. That is why we are checking here. That is the only, and you can see these statements are exactly opposite to these statements. P of I is J, here we have P of J is I. That is parent of node J becomes parent of I. Here node I becomes parent of node J. Then we replace the weight of parent J, and in here we do it for parent of I. So here we have minus 3. Now else part comes, and here we have parent of J, that is parent of 3 will become I is 1. So 1 will become parent of J, that is parent of 3. So P of 3 instead of minus 1 will have 1. So what actually happens? 3 is here, 3's parent becomes 1. 3's parent is 1. Now we have to update, 1 is the root node, so we have to update root. So which is assigned the value as temp, that is P of I. I is the root, 1 is the root. So temp minus 3 is assigned here. So what this means now at this stage, that element here, this is minus 3. So tree with 1 as the root has got 3 nodes total. Whereas here minus 1 for 4. This is the disjoint check. This is only one element here. 5, root element 5, only one element. So this way, we can know that which tree has got more number of nodes. Then again, subsequent union operation, let's say union of 1, 4. So again here, P of I is P of 1, P of J is P of 4. So minus 3 minus 1 becomes minus 4. This is false. Then what we have is else part. Here P of 4, that is parent of 4, will become I is 1. Since in P index 4 we have 1 over here. So node 4 will be a child to node 1. And then node 1, that is the root, its value has to be updated. So P of I equal to temp, where we assign -4. That is, this tree now with root 1 will be having 4 elements. The same thing, 1 comma 5, if we do, 5 is getting assigned. Stuck away. 5, this becomes -5, and this is false, and we have 5, parent of 5 will become 1, that is I. So 5 will be assigned here, and then subsequently the P of I, which is 1, will become -5. That means it's going to have the total number of nodes are 5. So this is how, or this is what we call it as a weighted union. That is, instead of assigning its parent, instead of assigning the parents of each set we are trying to perform union, instead of assigning that to a parent, it's going to create a tree with a higher level. But in this case, if you look at this operation, if we have n number of nodes, then all nodes will be assigned to the tree which has got highest weight. So that means more number of nodes. So weighted union means, and how this is performed is, if you have two sets, one set with larger number of nodes, other set with small number of nodes, that is its weight is less, then the smaller root of the smaller set tree will become child of the first tree, and the level is maintained. So when the level is maintained, obviously subsequent find operations will, since the height of the tree is reduced, subsequent find operations, they will be very efficient. Now, even this weighted union, if you look at this time complexity of this weighted union, it's it will be primitive because there are no loops. So this weighted union also will be taking O of 1. So absolutely there is no problem with respect to the weight. I mean the performance of union, simple union and weighted union. Let us try to take another example. Let us try to perform operation 1 of 1 and 2, weighted union of set 1 and set 2. So 1 has become 1 has become the parent of node 2. Subsequently, the numbers are the numbers you can see in the array, it is changed. Weighted union of 3 comma 4. So 3 is the root node, 4 becomes its child. Then 5 comma 6, 5 is the root node, 6 becomes its child. And again we are calling weighted union of 7 comma 8. So 7 becomes its parent and 8 becomes its child. Now suppose we have these nodes. Subsequently, let us try to merge or let us try to perform union of 1 comma 3. Union of 1 comma 3 means this set is, both set has got, we are performing weighted union. So both sets have got same number of elements. So set 2 will become the child of set 1, because that is how the if condition is written. We are first checking that way. Then suppose if we perform weighted union of 5 comma 7, 7 will become the child of 5. Now suppose if we have to perform, subsequently you can see that the values in the P table or the P array is getting changed. You can trace yourself. Now subsequently if we perform weighted union of 1 comma 5, that is union of these two sets, set with root 1 and set with root 5. If we perform, what happens is root 5, the tree with root 5 becomes the child of tree with root 1. So this is how weighted union is performed, and some subsequently values are changed. You can look at these values later. Now its performance is 0, 1 because O of 1 because all the statements are primitive statements. Now this is the tree we got performing weighted union. Weighted union is very efficient, doesn't matter. Now let us try to talk about, and this is the table we got by performing this. If you look at this table, you can find that one P of 1 has got -8, minus because 1 is the root node, 8 because there are 8 elements or 8 nodes in that tree. That's why it's 8. And rest of the P of 2 is its parent, P of 4 means 3 is its parent, 6 means 5 is its parent. Now here, let us find 8. We are performing simple find of 8. So find of 8 means what happens? 8 is here. Now this 8, its parent is 7. Obviously, every find operation will return its root node of the tree which it belongs. So we go to 7, node 7. Node 7 has got 5 as its parent, so we go to the node 5. Then node 5 has got 1 as its parent. We go to root 1. 1 has got -1, so we stop here. So how many comparisons we had to make? 1, 2, 3, 4 comparisons to reach till the root node. Now, to optimize this, we note that simple find is takes O of n as the time complexity. To optimize this, we use a method known as collapsing find. The purpose of collapsing find is that whenever we try to find a node, it's a parent of that node element, we try to find an element. We say that subsequent find operation should result in a better performance. So collapsing find, we are passing 8, so I is 8. Now what collapsing find does is we take a variable r. This r is assigned as the parent, index of the parent, which is I. It's assigned the node index to the node, not the parent, sorry. And we have p of r less than 0 and r becomes I. This statement is same as what we have seen in simple find. Then this is 8, so 8's parent is 7, so we move to 7, so r moves to 7. So here we have, then again this while loop moves, so p of 7 is 5, so 5 is assigned to r, so r moves to index 5. Then again from 5 we have to move, 5 is having 1, so r is assigned 1, so we move to 1. And finally we stop here. We don't look at -8 because -8 greater than 0 we are seeing. We stop here. We don't move further. So we actually found r, that is the index of the the parent of 8. We found the parent of 8. That was, we returned it in simple find. But here what we do is we collapse this. So if while I not equal to r, what is I? I is 8. That is what we started with, 8th node. Not equal to r. R became 1. R actually was equal to I, but r became 1. We have a while loop where we use as variable p of I. P of I is 7. So 7 will be stored. So r, which is 1, is assigned to p of this I, which is 8. So 8, we are collapsing 8. So 8 value over here will be 1. So what we are doing is we are making node 8's parent as, instead of 7, we are making as 1. Then we assign s to I because we have to shift those variables. So I becomes s. Now I becomes 7. I becomes 7. So what we have to do again, value while loop is true. So we make 7. You can trace these all these values. I'm showing you here. 7. We are collapsing 7. So 7's parent will also become 1. And 5's parent will also become 1, though it's 1 itself, so it doesn't matter. So what actually we have done is what we made parents of each node on the path till the root. All those nodes parent, we made it as 1. So if we go back, if you look at this, what all the nodes, node 8, node 7, node 5 on this path, we have collapsed all these nodes and made the parent of those nodes at the parent of the element we are finding. So 8th node became, we have collapsed it. Instead of parent as 7, we collapsed it as parent as 1. Node 7, we collapsed it and made it as 1. And even node 5, we made it as 1. So subsequent find operation for 8 will be very efficient because you only have to make one comparison. So this is how collapsing find works. Collapsing find, its time complexity is same, O of n, as Collapsing find value is O of n because there are two loops which will run at most for n number of times. So there is no change in the time complexity of collapsing find, except that with respect to simple find, except that every time we find a node, we make all the nodes on that parent of all those nodes on the path as its root node. So that is what is union and find operations. We have seen simple union, simple find, collapsing weighted union, and collapsing find. So these are this was all about sets and disjoint set unions. So Anya, oh sorry, it's 11:03. The time is over. If you have any questions, just ask me, or we can end this class. Now this was the end of the first unit, and in the next class we will be starting with the second unit. So if you have any questions, just type in the chat box, or we can continue in the next class. Now I'll be uploading this video and last video also. Last class's video I have not uploaded in the classroom. If you, for your reference, I mean, you can go back and check if you have any doubts or questions. You can replay these videos. Now there is a question here, sir. If there are two O of n, it should be O of n square. No, those two of O of n are not nested loops. One loop is there. After that, we have second loop, subsequent loop. So if they are nested loops and each loop runs for n times, then it will be O of n square. But we have a loop, that loop completes in O of n times. And then we have a second while loop which completes in O of n times at most. So this will be 2 times O of n, which is nothing but O of n itself. It's not O of n squared. Okay. Any other question? Okay, no problem. Thank you very much. You can log off.